Our next presenter is Dr. Wil Srubar. He is an associate professor of civil and architectural engineering and material science at the University of Colorado Boulder. Dr. Srubar holds a PhD from Stanford University. His research integrates biology, polymer science, and cement chemistry to create low-carbon, biometric, and living materials technologies for the built environment. To date, his laboratory has received over $8 million in sponsored research funding through the U.S. National Science Foundation, Air Force Research Laboratories, ARPA-E, and DARPA's Biological Technology Offices. So with that, thank you, Dr. Srubar. I will turn it over to you.
Thanks, Sam. Hi, folks. Good morning, good afternoon, or evening, depending on where you are in the world. As Sam mentioned, my name is Dr. Wil Srubar. I'm an associate professor at the University of Colorado Boulder. Really happy to be here today, speaking in this panel and taking the opportunity to share a bit about our $1.2 million ARPA-E funded project, which began a few years ago in collaboration with Claire White's group at Princeton, which really concerns acid-resistant alkali-activated geopolymer cements, specifically engineered to enhance the performance of sewer infrastructure. For those of you unfamiliar with geopolymer cements, geopolymers really is a term that describes a subset of alkali-activated cements in which we use an aluminosilicate that is not fly ash or slag, but rather a calcined clay, such as metakaolin, that is really low in calcium or even calcium-free in our case, which is really mechanistically the key to its performance in sewer environments, and as I'll explain in a few minutes. We produce these geopolymers by activating metakaolin with an alkaline activator like sodium hydroxide supplemented with sodium silicate. So unlike ordinary Portland cement, where you get calcium silicate hydrate and calcium hydroxide as the reaction products, geopolymers really produce predominantly a sodium stabilized aluminosilicate hydrate. And so there's really no calcium in the system. Our primary goal, of course, is to solve the problem of biogenic sulfuric acid degradation of ordinary Portland cement concrete. So we've heard a lot about this problem from the previous two speakers. What I do want to point out here is in the lower left-hand corner, in terms of the mechanism, is that the sulfur-reducing bacteria in the wastewater produce this hydrogen sulfide gas. The acidophilic bacteria, really the sulfur oxidizing bacteria, convert that H2S into sulfuric acid. The sulfuric acid can react with the calcium-rich phases in ordinary Portland cement, like calcium hydroxide, and the acidic environment leads to decalcification and the degradation of calcium silicate hydrate. And that really is the cause of that gypsiferous layer that we see that can form on the crowns of sewers. It's really quite weak and quite friable. So this is really a classic example in which low calcium alkali activated materials like geopolymers might be the better material solution to this problem. And we're not necessarily interested, in replacing the whole pipe completely. Geopolymer coatings, though, could extend the service life of sewers substantially, as we'll show here in a few minutes. There are certainly other material solutions to wastewater infrastructure like metal, polymer, clay pipes, but really none are as ubiquitous as ordinary Portland cement concrete. And in terms of material solutions, you've heard the previous two speakers talk about antimicrobial cements as one avenue to mitigate this problem. Really, our solution is to engineer a geopolymer coating material that it can exhibit an 80% reduction in that biodeterioration rate, namely that production of the gypsiferous layer from about 5 millimeters a year to less than 1 millimeter per year, thereby extending the service life of our sewer infrastructure. And really, we want to show through our project that we're seeing reductions in total life cycle environmental and even economic costs of mitigating the sulfuric acid degradation. So just a quick bit about our team. Very honored to be leading a talented team of postdocs and graduate students with my co-PI, Claire White. My specialty, as Sam said, is really in biological materials and alternative cements. And so this project really takes a look at biogenic acid production and trying to understand how materials can coexist in harmony, even with those bacteria present. We're really building on a previous National Science Foundation award that I received, where we found that if you take geopolymers and dope them with certain cations, we can actually achieve really unprecedented improvements in the sulfuric acid resistance of those materials. And Claire's group really specializes in complex and heterogeneous submicron structures and processes. You'll see that she's done a lot of molecular dynamic simulations for us to help us understand really what's going on during the degradation when we expose these materials to sulfuric acid. So our project objectives are depicted in this schematic. Really, our first goal was to experimentally establish benchmarks for sulfuric acid resistance and desirable mechanical properties. And this project is a couple of years old already, so we really went right to sulfuric acid immersion as our metric for sulfuric acid resistance. Because again, we're not looking at antimicrobials, we're just really trying to understand the performance of these materials in a sulfuric acid environment. And that subset of that first goal was to benchmark the performance of geopolymer cements and to demonstrate the superiority of those geopolymer binders in sulfuric acid. And then the second goal that we have is to maximize sulfuric acid resistance through the doping of these geopolymer cements with certain cations. Because we have found experimental evidence, and even I'll show you some computational evidence that these strongly bound cations can stabilize the geopolymer frameworks even in acidic environments. We do have a third goal, of course, of substantiating the improved economic and environmental life cycle costs through LCCA, life cycle cost analysis and life cycle assessment. So here I'm showing the results of our very first benchmarking effort, where we were looking at samples of type 1,2 and type 2,5 Portland cement for compressive strength, porosity, and setting time. Again, we were trying to benchmark these materials and ensure that we were achieving desirable properties like greater than 15 megapascal compressive strength, less than 40% porosity, and less than 24 hours of setting time. And of course, with all of these materials, they certainly passed our initial benchmarks for fresh and hardened state properties. We then tested a variety of several mixes of geopolymer cements. I am keeping the exact details of the formulation a little obscure since we have some IP in progress and we haven't yet published our results. But these are all unique formulations of geopolymers. And as you can see, there were several mixes that passed our compressive strength, porosity, and initial setting time tests. And so those were selected for further study just based on, 3 of them were selected based on this initial benchmarking of just these initial properties. One note about setting time, sometimes geopolymer cements, people think that you need heat curing to get them to set, and that is not necessarily the case. These were all set within 24 hours with ambient conditions. So it really just comes down to designing the geopolymer cement paste correctly to achieve that performance. So we selected 3 of these to move forward in our sulfuric acid degradation experiments. And so what I'm showing here is the one-dimensional corrosion depth measurements of cylinder samples of all of the formulations that we tested, including our 4 ordinary Portland cement paste controls in comparison to our geopolymer cements. So these samples were exposed on one surface only, one face of the cylinder in a pH 2 sulfuric acid solution for 7 days, just to get a relative comparison of that corrosion depth. And so you can, so we were able to measure the depth of that sulfuric acid degradation on each sample after 7 days of exposure. In terms of the ordinary Portland cement controls, the type 1-2 samples provided the best performance. This is important because some folks might think that a type 2-5, which is a sulfate resistant cement, would perform better, but really resistance to sulfate attack, the exposure to sodium sulfate in groundwater does not necessarily ensure resistance to sulfuric acid in sewers because it's an entirely different mechanism altogether. So really we found our type 1-2s to be better at resisting the sulfuric acid comparatively. But in terms of the geopolymer cements, you can see that formulation number 2 exhibited the best performance in the sulfuric acid testing. And it's clear from this result how much better low calcium geopolymers can be at resisting sulfuric acid attack. Now, there were unique performance benefits to each of these formulations. So we did end up moving them all forward to the next phase of our research plan, which was to enhance the performance of these cements by cation doping. So as I mentioned, previous research in my lab by my PhD student, JP Javadhan, indicated to us that when we dope the geopolymer cement with specific cations, that we could actually stabilize the sodium, the Nash gel upon exposure to sulfuric acid. So the question for us was, well, which cations would work best? And so we wanted to know, really from a fundamental thermodynamic perspective, which cations are the best at stabilizing the geopolymer framework. So Claire White's group did a really terrific job at running molecular dynamic simulations to calculate the binding energies of different stabilizing cations inside of the cement paste that would charge balance the SiO-Al bond. So I'm showing you here this inset. Sorry, the video won't be able to play because this is a PDF, but this blue dot here is really sodium. So this is typically sodium in regular geopolymers, which can, upon exposure to sulfuric acid, be ejected due to the hydronium ions that are entering the system due to the acid attack. And we can also get ejection of the aluminum if the sodium leaves the system as well. So what we were doing is trying to understand if we replace that sodium with a different cation, would the binding energies be improved and help stabilize the very fundamental aluminosilicate bonds here. And so we found, we selected 4 cations based on the different binding energies, again, based on performance and also cost and availability of these different cations. And I apologize, again, we're keeping this a little bit obscure just because we just haven't really published on this quite yet. So we selected these 4 cations that to us worked from a computational standpoint. How did they work experimentally? So here is a graph, again, showing the 7-day corrosion depth of the mixtures we tested in sulfuric acid. We are comparing the performance of all of the geopolymer mixes that we tested to the OPC type 1-2 control as our benchmark, because that was the best performing. And I want to explain the nomenclature we're using here. So the first number is the mix ID without the cation. So this is mix number 2. And then the second number is the cation ID that we use. This is 1 through 4. We've selected 4 cations. And then A or B was the cation dosage, whether it was high, medium, high, medium, or low, A, B, or C. And you can see from these results that some of the cations worsened the performance, and we have theories as to why, but you can also see that cation number 2 improved the performance even at low and kind of middle concentrations. So it exhibited on average an improvement compared to the original formulation. We didn't test all cations at all dosages because we used really a design of experiments to minimize the total number of samples. But we did test cation additions to mix number 3. And again, cation number 2, mystery cation number 2 was the best performer, whereas the other cations did not show enhanced sulfuric acid resistance. And then the same was true with mix geopolymer, the original mix number 6, where again, cation number 2 prevailed. So really the main takeaway for us up into this point was that geopolymer formulation number 2 With cation number 2 is our winning formulation compared to our OPC benchmarks. As we've shown, it decreased sulfuric acid corrosion depth by up to 99%, whereas our original goal was to decrease that by 80% according to our experimental methods. The next question we get is usually about, I'll go here. The next question we usually get is about cost. So Claire's team also built a preliminary cost model to compare our geopolymer coating with leading conventional materials used in sewer infrastructure, namely, entirely new OPC pipe, concrete pipe, and polymer-based materials to line sewers. And you can see that if we built a 100% geopolymer pipe, it would be more expensive upfront than a concrete pipe. But if we simply shotcrete a geopolymer coating onto existing pipes, we can see that the cost of that application decreases and becomes a very attractive option. If we go to normalize the cost per year of service life, which we can estimate based on we have some preliminary estimates of how long these coatings are anticipated to last. We haven't taken into account any discount rates in this calculation, but this gives you just a quick idea that a geopolymer coating with our formulation would again be a very attractive option. So with that, we're actively looking for licensing and commercialization partners. We have about 6 months left in our project, so there's ample opportunity for industry engagement to help us refine and strengthen our tech to market strategy. So feel free if you'd like to reach out, if you'd like to learn more and to get involved in our project, because we think we have something pretty special. So thank you to Sam for allowing us to share our results with you, and a big thank you to ARPA-E for funding our project. With that, I'll take any questions, or if we're over time, Sam, we can move on to the next speaker.
Thank you, Will. And my apologies, I went to turn my microphone on and it was already on. I have 2 questions that have come up. First question from Robert Shilton: why was compressive strength a benchmark criteria? And if it does not have a significant impact on acid resistance, MIC resistance?
Yeah, we went ahead and tested compressive strength because we anticipated that that's a data point that many folks in the industry would want to see, and so we just wanted to go ahead and select it. We also had some porosity benchmarks as well, but what we're finding is that porosity is not necessarily a good indicator. Just like compressive strength, it's not necessarily a good indicator of acid resistance. To that second part of the question, it really just comes down to the chemical reactions that are occurring, and whether or not the material itself can buffer that pH, but also just maintain its stability in the low pH environment.
Great, thanks, Will. Got one more question from Doug Hooten. Wouldn't shotcrete linings have a rough surface and increased biofilm formation?
Sure, absolutely, unless you would go ahead and finish that to be smooth. I will point out that our materials, because it's not an antimicrobial mechanism, we don't necessarily anticipate the bacterial forming and thriving on the surface to be that big of a problem if we can resist the sulfuric acid that's being generated. So that's why we went straight to that kind of stage 3 simulation where we're placing our materials in sulfuric acid, because whether the bacteria are there or not, we just want to engineer a material that can be acid resistant. So really the surface roughness won't come into play that much.
Great, yeah. One more question and then that'll be it. This is from Tyler Walker, are you able to comment on CSA cements and MIC resistance?
We might have a presentation on CSA cements, or maybe it's CACs. I can't remember. But the fact of the matter is that there's calcium in those systems, and so I don't know very much about it. But my hunch is that at lower pHs, if it does become decalcified, that calcium's free to react with the sulfate that's produced in the sulfuric acid. So My hunch is that you would see some expansion products that might form, but I don't know. I don't know the specifics about that.
All right, so there was one more question. I'm looking here, maybe a question that was answered. So pardon me here, just 1 second.
I've got it here. It says, do geopolymers behave in a similar manner or only in phase 3?
We haven't directly tested them in phase 1 and 2, kind of related to the other question about surface roughness. So the colonization, we might actually see some benefits related to the ability to resist that stage 1, stage 2, in comparison to ordinary Portland cement. We just haven't tested it. We haven't tested that.